Hi, I'm Malingrai Jyoti. So today I'll be talking about software techniques for shared cache multi-core systems. I'll be dealing with the shared cache architecture with a special emphasis on Intel's advanced smart cache and few techniques which could be employed for using the cache effectively in the multi-core systems. Let's see what is cache. If we observe the processor memory performance growth curve over the past 5 to 6 decades, there is a growing imbalance between processor and memory performance in terms of latency. So this gap basically limits the processor performance. One solution is to employ a faster memory space wherein frequently accessed data or instructions are stored so that the processor can use these items to fasten its execution. So that memory is called the cache. In a typical multi-core processor system, the cache is usually organized into three layers: the L1 level, the L2 level, and L3 level. The L1 is very close to the processor, whereas L3 is very close to main memory module. So this is a typical memory organization in multi-core processor system. In the multi-core processor system, we can have the last level cache shared between all the other cores. So we can see the concept of shared cache architecture in this case also. This 8 MB L3 cache is shared between the four processors of i7, four cores of i7 processors. Now let's see what is dedicated cache versus shared cache. Over the past decade, the trend is moving from the single core to the multi-core processor system, as a result of which the computer architectures have got several options to organize one of the most important resource, that is a cache. Some architectures keep the last level cache dedicated only for one processor, and some other architectures keep the last level cache shared between all the other cores. So as a result of which we have got dedicated cache and the shared cache. Intel uses advanced smart cache technology in all the processors starting from Intel Core 2 Duo, which was introduced in the year 2006. So this diagram depicts two cache architectures. One is the shared cache architecture, the other one the dedicated cache architecture. In the shared cache architecture, whenever the core 1 is idle, the core 2 can use the shared space for its operation, as a result of which it leads to higher cache hit rate and lower cache miss rates. And it will also leads to reduced bus traffic and lower latency to the data. Whereas in the dedicated cache system, whenever the core 1 is idle and core 2 is active, the core 2 can access only the allocated space, as a result of which the cache underutilization is prominent in the dedicated cache architecture. The shared cache architecture has got several advantages. First is it leads to efficient usage of the last level cache, and it leads to flexibility for the programmers, wherein it allows more data sharing opportunities for threads running on separate cores that are sharing the cache, and it also provides an alternative communication mechanisms between the cores, and it will reduce the data storage redundancy. The same data only needs to be stored in one space, and it will also reduce the front side bus traffic. The effective data sharing between the cores allows data requests to be resolved at the shared cache level instead of going all the way to the system memory. So as a result of which the front side bus traffic will be reduced. So this is about the advanced smart cache. So let's deal with the software techniques which can be used to make shared cache an effective device. The shared cache architecture brings exciting new opportunities to software and system designers. As mentioned in the beginning, let's see some well-known techniques for using the cache effectively. So let's deal with the processor affinity at first. So let's see what is a thread. In a multiprocessor system, a thread is a single line of commands that are getting processed. Each application will have at least one thread. It can be thought of as a road or a highway through which the information is passed to the core. Now, the processor affinity is a feature in the multi-core environment through which a thread or a process can be assigned to execute only on a designated or a specified processor or a range of the CPUs. So without this facility, the thread or the applications may get assigned to wrong processors or the cores, which may lead to possible degradation in the performance. So thus, it may be worth to consider to assign contention-only threads, that are the threads not sharing any data but needs to use cache, to the cores that are not sharing the cache. Also, the data sharing threads can be assigned to cores that are sharing the cache. Also, it can be assigned to the same core. So this slide shows a simulation results of two tests. The first test, in which the two threads are assigned to core 0 and core 1, and the two threads are data sharing threads. And the second test is performed by assigning two threads to a single core. The first test, so in which the data sharing threads were assigned to two different cores, got us a higher percentage of misses compared to the data sharing threads which are assigned to the same cores. Thus, the processor affinity will play a significant role in improving the performance of multi-core systems. So let's see what is cache blocking or data. The cache blocking is a well-known optimization technique that can help avoid memory bandwidth bottlenecks in a number of applications. The key idea behind cache blocking is to load a small subset of a much larger dataset, then work on this block of data in the cache. By using or reusing this data in the cache, we reduce the need to go to the memory all the time. So thus, this technique will allow the data to stay in the cache while being processed by the data loops, as a result of which a better cache hit rate is achieved by reducing the unnecessary cache traffic, that is fetching and evicting the same data throughout the loops. So let's see some simulation results. So in this example, which is done without cache blocking, the B of J array is loaded at each iteration from the main memory. Okay, and with cache blocking, so this B of Y will be used to calculate all the possible cases, and only then the next iteration will be called. Thus, by using this method, the cache traffic is reduced and cache hit rate is improved. Now let's see what is a hold approach. So this approach tries to reduce the frequency of access to the shared data by letting each thread to maintain its own private copy of data and allowing to update shared copy only when necessary. So this basically reduces the traffic in and out of the shared cache. So in this diagram, the thread 0 and thread 1 update the shared data copy frequently, resulting in more traffic in and out of the shared cache. While in the other case, the threads are more disciplined in terms of accessing the shared copy by only updating it when necessary. So one way to achieve this is to maintain a private data copy for tracking until all the updates have to be done to the shared copy. Now let's see what is fault sharing. The fault sharing is a common problem in the multi-core processor system. Basically, it happens when the threads on the different cores write to the shared cache line but not at the same location. So in this example clearly depicts what is a fault sharing. The CPU 0 and CPU 1 has got the same cache line, that is block J, in their local cache. So whenever CPU 0 tries to modify this K term and CPU 1 tries to modify K plus 3 in the future, the fault sharing will come into picture. So whenever CPU 0 wants to modify K, it will invalidate all the lines which are present in the other cores, as a result of which whenever CPU 1 tries to access that particular line in future, it will make the block J present in the CPU 0 to go to the main memory and then fetch from the main memory and load into its own cache. So this is called the fault sharing concept. This can be avoided in n number of the ways. Then if we allocate non-shared data to different cache lines, the fault sharing can be avoided. And if you think about splitting the cache line into sub-blocks and assigning each sub-block a dirty bit, this fault sharing can be avoided. And also, moving the threads to same core can be a solution for the fault sharing. Thus, thanks for watching the video. Thank you.